Class notes. Characteristics and physical properties of group 15 element. Class 12 Chemistry P block elements. Contains representative elements or the main group element. Group 15 element. General characteristics of group 15 elements. Atomic and physical properties. Oxidation states, negative oxidation state, positive oxidation state. Representative elements or the main group element. In the long form of the periodic table, the elements have been classified into 4 blocks S, P, D and F depending upon the subshell in which the last electron enters. The elements belonging to S and P blocks in the periodic tables are called representative elements or the main group elements. They belong to group 1, 2 and from 13 to 18. The elements belonging to groups 1 and 2 belongs to S block and have the general configuration NS12. The elements belonging to the group 13 to 18 belongs to P blocks and have the general configuration NS2 and P1 to 6. Group 15 elements. It contains 5 elements, namely nitrogen, phosphorus, arsenic, antimony and bismuth. This group is regarded as nitrogen family. Occurrence. Molecular nitrogen comprises about 78% by volume of the Earth's atmosphere. It is not very abundant in the Earth's crust. Since nitrates are very soluble in water, so these are not widespread in the Earth's crust. The only major nitrate minerals are sodium nitrate and potassium nitrate. Nitrogen is also an important constituent of proteins, amino acids and nucleic acids in plants and animals. The continuous interchange of nitrogen between the atmosphere and biosphere is called nitrogen cycle. Phosphorus is the 11th element in order of abundance in crystal rocks of the earth. All its known minerals are orthophosphates. The common minerals of phosphorus are phosphorite, calcium phosphate, fluoropatite, chlorapatite, hydroxypatite. Phosphorus is essential for life, both as a structural material in animals and plants. It is present in bones as well as in living cells. About 60% bones and teeth are calcium phosphorite or fluoropatite. It also occurs in nucleic acid, DNA and RNA, which control the hereditary effects in human beings. Phosphorus is also found in ATP, adenosine triphosphate, and ADP, adenosine diphosphate. The elements arsenic, antimony and bismuth are not very abundant. These are obtained as metallurgical byproducts from roasting sulfide ores. General characteristics of group 15 elements. Electronic configuration. Nitrogen, atomic number 7, electronic configuration. Helium 2s2 2p3. Group number 15, period number 2. Phosphorus, atomic number 15, electronic configuration. Neon 3s2 3p3. Group number 15, period number 3. Arsenic, atomic number 33, argon 3d10 4s2 4p3, group number 15, period number 4. Antimony, atomic number 51, electronic configuration krypton 4d10 5s2 5p3, group number 15, period number 5. Bismuth, atomic number 83, xenon 4f14 fd10 6s2 6p3 15 6. The atoms of group 15 have 5 electrons in the outermost shell, 2 in S and 3 in P subshell. The general electronic configuration of this group may be expressed as NS2NP3. Atomic and physical properties. Atomic and ionic radii. The atomic and ionic radii of group 15 elements are smaller than the atomic radii of the corresponding group 14 elements. On going down the group, the atomic radii increases with increase in atomic number. Explanation. The nuclear charge in case of elements of group 15 is larger than in the case of elements of group 14. Due to increased nuclear charge, the electrons are strongly attracted by the nucleus and therefore atomic radii decreases. Thus, the atomic radii of elements of group 15 are less than those of group 14. On moving down the group, the atomic radii increases due to increase in number of shells because of addition of a new principal shell in each succeeding elements. However, from St9 to bismuth, only a small increase in covalent radius is observed. This is due to the presence of completely filled d and or f orbital in the heavier members. Ionization enthalpies. The first ionization enthalpies of the group 15 elements are higher than the corresponding members of the group 14 elements. On going down the group, the ionization enthalpies decreases. Explanation. The larger ionization enthalpy is due to greater nuclear charge, small size, and stable configuration of the atoms of group 15 elements. The electronic configuration of atoms of group 15 are half-filled, NPX1, NPY2, NPZ1, and are stable. Therefore, they have high ionization enthalpies. The decrease in ionization enthalpy as we move down the group is due to increase in atomic size and a screening effect which overweigh the effect of increased nuclear charge. Electronegativity. The electronegativity values of elements of group 15 are higher than the corresponding elements of group 14. On going down the group, the electronegativity value decreases. Explanation. The elements of group 15 have a smaller size and greater nuclear charge of atom and therefore they have higher electronegativity values. The decrease in electronegativity on going down the group is due to increase in size of the atoms and shielding effects of inner electrons shells on going down the group. Metallic character. The elements of group 15 are less metallic. However, on going down the group, the metallic character increases from nitrogen to bismuth. For example, nitrogen and phosphorus are non-metallic. Astatine and antimony are partly non-metallic, while bismuth is a metal. Explanation. Due to increased nuclear charge and higher electronegativity, the elements of group 15 are less metallic than the corresponding elements of group 14. On moving down the group, the atomic size as well as the screening effect of the intervening electrons increase. As a result, the ionization enthalpy decreases and therefore metallic character increases down the group. Melting and boiling points. The melting points of group 15 elements first increases from nitrogen to arsenic and then decreases to antimony and bismuth. However, the boiling point increases regularly on going from nitrogen to bismuth. Explanation. The melting points increases down the group due to increase in atomic size. However, the unexpected decrease in the melting points of antimony and bismuth is because of their tendency to form 3 covalent bonds instead of 5 covalent bonds due to inert pair effects. As a result, the attraction among their atom is weak and hence the melting points are low. Because of large size of atom, bismuth has still weaker interatomic forces than antimony and therefore has still lower melting points. The boiling points increases down the group from nitrogen to bismuth because of increase in their atomic size. Catenation. The elements of group 15 also show a tendency to form bonds with itself, self-linking of atoms known as catenation. For example, hydrazine has two nitrogen atom bonds together. Hydrozoic acid has three nitrogen atom. Azide ion has also three nitrogen atoms bonded together. Among the elements of group 15, phosphorus has the maximum tendency for catenation, forming cyclic as well as open chain compounds consisting of many phosphorus atoms. The lesser tendency of elements of group 15 to show catenation in comparison to carbon is their low MM bond dissociation enthalpies. Allotropic. Except nitrogen and bismuth, all other elements of this group show allotropic. For example, phosphorus exists as white, black or red phosphorus. Arsenic exists as yellow or grey arsenic. Antimony exists as yellow or silvery grey allotropic forms. Oxidation states. The elements of group 15 have 5 electrons in their valence shell. They exhibit various oxidation states from -3 to +5. Negative oxidation states. These elements have 5 electrons in the valence shell, NH2 and P3, and therefore require 3 more electrons to acquire the nearest noble gas configuration. But the gain of 3 electrons is not energetically favorable because it requires very large amount of energy to gain 3 electrons and form M3- ions. Nitrogen, being the smallest and most electronegative element of the group, forms N3- nitride ion and shows an oxidation state of 3 in nitrides of some highly electropositive metals such as magnesium Mg3 and 2, calcium Ca3 and 2, etc. The other elements of this group form covalent compounds even with metals and show an oxidation state of -3 with metals. For example, calcium phosphide, sodium arsenide, zinc antimonide, magnesium bismuthide. The tendency of the elements to exhibit -3 oxidation state decrease on moving down from phosphorus to bismuth due to increase in size and metallic character. The last member of the group, bismuth, hardly forms any compound in -3 oxidation states. In addition to -3 oxidation state, nitrogen and phosphorus show oxidation states of -2 in hydrazine and diphosphine respectively. Nitrogen also show an oxidation state of -1 in hydroxylamine, but phosphorus does not. Positive oxidation states. All the elements of group 15 exhibit positive oxidation states of +3 and +5. However, on moving down the group, the stability of +5 oxidation state decreases while that of +3 oxidation state increases due to inert pair effect. Because of energy consideration, these elements cannot lose all the 5 valence electrons, therefore they do not form M5+ ions, and all the compounds of group 15 elements having +5 oxidation state, that is PF5, PCl5, SBF5, BAF5, are essentially covalent compounds. Nitrogen does not form compounds in +5 oxidation states such as NF5, NCl5, etc. because it does not have vacant d orbital in its valence shell, which can enable it to extend its octet. The stability of the highest oxidation state +5 decreases down the group. The +5 oxidation state of bismuth is less stable than in antimony. This is due to inert pair effect. The elements of group 15 form both covalent, for example NCl3, PCl3, ASCl3, SbScl3, and ionic compounds, for example BiF3, SbF3 in +3 oxidation state. The +3 oxidation state becomes more and more stable on moving down the group. Nitrogen and phosphorus also show oxidation state of +4 because of the ability of one lone pair on NH3 and PS3 to form dative bonds with Lewis acid. However, nitrogen can exist in various oxidation states from -3 to +5 in its hydrides, oxides, and oxoacids. Phosphorus also exhibits +1 and +4 oxidation states in some oxoacids. In nitrogen, all oxidation states from +1 to +4 tends to disproportionate in acid solution. In phosphorus, nearly all the intermediate oxidation states disproportionate into +5 and -3 both in acid and alkali solutions. The maximum covalency of nitrogen is restricted to 4 because it does not have vacant d orbital in its outermost valence shell, n equal to 2. Therefore, only 2s and 2p's orbitals are available for bonding, and it cannot extend its valency beyond 4. That is the reason why nitrogen does not form pentahalides such as NF5 or NCl5. On the other hand, phosphorus and all other elements have vacant d orbitals in their valence shells and can use all their valence orbitals to exhibit covalency of 5 or 6. For example, PF5, PCl5, ST9F5 and PF5, PF6 minus or SBF6 minus, etc. Filed under Chemistry, Class 12, the P block elements. About Mrs. Shilpi Nagpal, author of this website. Mrs. Shilpi Nagpal is MSc Honours Chemistry and BSc Honours Chemistry from Delhi University, B.Ed, and has many years of experience in teaching. She has started this educational website with the mindset of spreading free education to everyone.